Okay, so algorithms for big data, we continue our discussion in the external memory model. So hopefully you guys remember what the external memory model was. You have an external disk, which is infinite. All the data is stored here. And you have this main memory, the CPU. And in the external memory model or the disk access model, we count how many times we do these block transfers, right? So in traditional algorithms, we minimize the CPU computation time. But in external memory algorithms, we don't care about the CPU computation time. We care about how many times we bring in stuff from external memory into our main memory, right? Which is the slowest step in this above figure. So that's what this red arrow is trying to indicate. And we bring the stuff in blocks of size B, right? So that's so all the algorithms have parameters B and M, right? Okay. So we had all this. Last class we were talking about search, right? And I told you that the analog of linear search in external memory would be an N over B IOs, right? And now, if the data is sorted, then you can use a B tree, which is log base B of N IOs, right? That's sort of the analog for binary search, which is log N. Here you don't get, you don't get log N over B, but you get a log base B of N. So that's for searching, if you're searching for an item in a sorted list. And if I give you a data that's unsorted and your job is to sort it, then, well, you can do one or two things, right? You can either insert into a B tree. So do people understand how I'm getting this time bound? Can anyone tell me how I get this time bound? Okay, you guys need to respond, otherwise I don't know whether you guys are understanding anything. So how do you sort in this time bound?
Someone wrote the answer in chat.
Right, Aiden, right. So you do search operation for n items, but in a B tree, you can not only search, but you can also insert, right? So you can just insert your n items one by one into a B tree, and at the end you have the sorted list. So however, this is not the optimal sorting time in external memory. The optimal sorting time in external memory is this, which is an algorithm that we'll see today. It's called multi-way merge sort. I was told that this algorithm is taught in databases. How many people have seen a multi-way merge sort in the database course? Has anyone here taken the database course?
Yeah, I remember learning about that a little bit in databases.
Okay. So it is apparently taught in the database course, but we'll see it again, right? But first, the B tree, which we had already discussed last time. So we can forget about this part. This is a lower bound. So the B tree was invented by Bayer and McBride. So I had described this to you the last time, right? So the root block has B equally spaced elements from your sorted array, right? And then for each subproblem, you put the B equally spaced elements and you put them in a block, and those are the children of the root. And in general, for every node of B pivots, these B pivots partition the area of this node into B plus 1 chunks. And for each of those chunks, you bring in B equally spaced elements, right? So the last level would basically have every Bth key, right? So you do every Bth key, every B squared keys, every B cube keys, and so on. Are there any questions about what a B tree is? So if not, how many levels does a B tree have? Like the root has the whole space, right, of the entire set of keys. And you're putting B equally spaced elements from this entire set of keys, right? So now what is the size of each chunk? On the first level, what is the size of the problem corresponding to a child on the first level?
Is it n over b plus 1?
Right. So n over b roughly, right? So for on the first level, each of them has a size n over b. I mean, the subproblem for a node has size n over b. And what do? We bring in b equally spaced pivots from that subproblem, and we put it in a block. And that block is the first child of the root. And now those b pivots from this first child, they partition that n over b size search space into n over b squared, right? Because each of them will divide it further by b. So what's the height of a B tree? So we stop when the search space is the size of a block, which is B. So I'm dividing n by B until I get B. So that's log base B of n. Right, so we did this last class. And now searching is pretty obvious, right? When you're searching for a key, you just follow the pointers and you'll either find it in the sorted set or you won't. Right? So here is a more detailed picture. I'll let you guys stare at it. So this was the n over b plus 1 spaces that I was talking about on the first level. So these correspond to the child of the root, right? So each of these chunks correspond to a child of the root. And now from these chunks, you will bring in b equally spaced pivots, and that will be the block of that child. Right? Okay, so here's a question. How much space do all the blocks on the first level take? What is the total size of all the children of the root? No, so Aiden, what I mean is, again, so the children of the root are blocks, right? We cannot store n stuff in a block. So remember, the B tree is a tree where every node is a block of B elements. They correspond to some search space, which is large, but in the block, we can only fit in B elements. Does that make sense or no? Right, like the root is one block and it corresponds to the whole search space. The left child of the root is one block, which corresponds to this size search space, the leftmost space of size n over b plus 1. So there are b children of the root, each of them is a block. So the first level needs b blocks or b squared total space, right? And the second level similarly will have b cube space. The fourth level will have b to the fourth total space or b cube many blocks. So I'm counting all of this to ask you, what is the total space taken by a B tree? So you'll sum these numbers, right? 1 plus b squared plus b cube and so on, up until the last level. What kind of series is this called?
That'd be geometric.
Right. And so if I have a geometric series, what is a simple way to upper bound it? So 1 plus 2 squared plus 2 cube, right?
A over 1 minus r.
Sorry, say that again.
A over 1 minus R.
A over 1 minus R. Well, so R is your ratio. So you're talking about an infinite series, right?
Yeah.
Yeah, but this has to be finite because I mean, these are all great. Okay, so if I have that, right, then one simple thing is that this is less than 2 to the 11. Any series is always less than its next term. Does that make sense?
Yeah.
And you can either write down the formula on the left and figure it out, or there's a pretty simple way to also figure this out. So it's always less than the next term, and I have 1 plus b squared and so on. The point is the entire space is basically dominated by the last level, but the last level has n over b blocks. So the total space taken by this is like 2 times n over b. So the space taken by a B tree is order n over b. Okay, because the last level dominates it. I mean, I don't know if someone told you this fact or not, but if you have a binary tree, right, how many nodes does a binary tree have in L levels? What is the total number of nodes in a binary tree in L levels? No, Daniel, it's 2 to the L. Right, but it'll be like 2 to the L, it's like 2 to the L plus 1, basically. Right, so that's all and what is 2 to the L plus 1? That is how many nodes you would have at the next level. Right, so that's all I'm saying, that the size of a binary tree is dominated by the number of nodes in the last level. So it's always less than twice the number of nodes in the last level. The same thing here. So that's the space taken by a B tree. And as we agreed, the searching cost is log base B of n, because that's how many levels you have, right?
Could you explain for the last level of the space of the last level of the B tree? So so you're counting the number of blocks in each level?
Yes.
Okay, so then I get that there's only one block in the root, and there are then in the second level, how many blocks do we have in the second level?
Right. So who can answer Gibeon's question? How many blocks are there in the second level? What does the root block do? Okay, what are the keys stored in the root block?
Well, the root block, isn't that divided in, like, split into B plus 1, like B plus 1 blocks, and then each subproblem gets split into another B plus 1. So like, would the second level be B squared blocks?
I guess by second level, yeah, so the total space will be B squared and there'll be B blocks. Again, it's called a B tree because every node has roughly B children or B plus 1 children. Right? So that's what I think you were also saying, right? Gibeon, does that make sense?
I think I'm a bit confused. So we have so the size of the root
No,
is
forget about
B
size.
because there is only one block.
What is the root? Root is 1 block, right?
Right. So the size of the root is B.
And what are those B keys?
So each slot of the block contains a pointer to the divider of the external memory.
Yeah, but what are those B keys? Which B keys are stored in the root?
Which B keys? Um,
The root is a block, right?
yeah.
What is in that block?
So, the data, I mean, the data in the external memory.
Yeah, but the data is size n, right?
Okay, yeah.
The block can only fit B things, right?
Mm-hmm. Mm-hmm.
So what are the B things in the root? Jonathan, that can't be, because how many keys would that be? If my data is size n and you store the start and end of every chunk of size B, then how many keys will you have? No, I'm confused. How you will have 2B? How many blocks does the data have? My data is an array of length n, and a block is an array, a subarray of size B. So how many blocks are there in the data? Right, that's n over B, right? So I can store the first element of every block in one block, right? My block can only hold B elements, and n over B is way more than B. Right? N is, as I said, terabytes. B is like whatever, megabytes.
Does it store a pointer to the block, to the data,
But which block?
to the start of each block?
But again, how many blocks do you have?
B over n. Oh, n over B.
N over B. So you would need that many pointers, right?
Yes.
Sorry,
That depends on n. I can only store B things.
sorry, Professor. My understanding, I could be wrong. My understanding is like we're breaking n into B blocks, and what I meant by we're storing like the star and the n, I meant we're storing like the star of each of those B blocks. But then you said that wouldn't work because we have too many star and
No,
n's.
because you're calling them a block. They're not a block, right?
Okay.
Because a block can only hold B elements. So what you mean is you have the whole n array, and you break it into B equally sized subarrays. Each subarray is length n over B plus 1, and the dividers of these subarrays, there'll be B of them, right? Because B of them, I have divided my whole array into B plus 1 smaller arrays.
I think maybe what I meant by like blocks, I mean like
These
suppose we
subarrays.
have a number from like a range from 1 to 10, and we're breaking it into twos. We'll be storing 2, 4, 6, 8, 10. That's what I meant. Like we're not storing the entire block, we're just storing the last element of each of those blocks.
So again, I don't think what I'm trying to say is a block by definition is a chunk of size B. My entire data is size n, right?
Okay.
So I think we're just mixing up the terminologies. Like when we say like dividing into blocks, I think we mean dividing into subarrays.
Right. Yeah. And I'm saying that terminology is confusing, because a block is always used for, like, we have a block transfer, right? So in external memory, the word block is always used for this B element. So the root node is a block of size B elements. It's not a subarray, right? What are those B elements? Those are the B elements that divide the whole space into, I mean, I don't know. When you do binary search, you take the middle pivot, right? Now you're allowed more pivots. You're allowed B pivots. So what is the common sense thing to do? Just place B equally spaced pivots in your whole array. Instead of doing a binary search, you're doing a B-way search. That's all a B trees. Does that make sense now?
Yeah.
Gibeon? Gibeon, does it make sense now or no?
Yeah, I got it. Sorry.
Mhm. So every time, so the root will store the B only, every node in the B tree is a block. So it only stores B elements. These B elements are B pivots somewhere in the whole data set. The roots pivots are those pivots that are equally distributed in the whole data set. Right? The left child of the root is a block of B pivots. Which are these B pivots? These are the B pivots that are equally distributed in the leftmost subarray of the root. That's why these subarrays keep dividing by a factor of B. We stop when the subarray fits in a block. And so we have log base B of n height of this B tree. Okay. And now how do you search? Well, you have some key X that you want to search in your data set. You first bring in the root block. So that's one IO, right? Because the root block is a block. Again, so this whole B tree is obviously not stored in internal memory because, as I said, the last level has n over B blocks and we can't store all of that in internal memory. So all of this B tree is pre-processed and then stored in external memory along with the point. So for every node, you store the pointers to the children in external memory along with the pivots. And now when you're searching for a key X, you bring in the root block. That's one IO, B pivots. You compare X to those B pivots. If X goes between two such pivots A and B, then you bring in the child of the root corresponding to this subproblem. And when I say bring in the child is also a block. So you'll bring in that block, compare it to X, branch to someone on the second level, and so on. So every time you bring in a block, you advance the level by one, right? And at the end of the day, you will locate X in some block, or you'll narrow down your search to one block, and then you just bring in that block, compare X to all the keys in that block. If you find it, great. If not, X is no longer there. So how many IOs did I do? How many block transfers did I do? Well, any key, any element X only compares to one block on each level, right? There's no way I'm bringing this block and that block because when I brought the root, I knew which side X would branch to. So the total number of IOs is basically the total number of layers because for every layer, I'm bringing in one block. And the number of layers log BSB of n, so that's my searching cost in IOs. Does this make sense? Any questions? So B tree search takes log base B of n IOs. If you have any questions, do speak up because the multi-way merge sort is going to be maybe more involved. So I need everyone to familiarize themselves with this external memory setting, and B tree is the first thing in this setting. So questions about B tree?
How much does the operation to calculate where the pointers are going to be cost?
Say that again?
Like, so at the beginning, we're kind of taking this B points to be in this place. Would that take all one time?
Ah, good. So actually you can build the B tree bottom up. So are you talking about the cost to build the B tree, right?
I guess, yeah.
Right. So that actually you can, so in the worst case, you can do it in n over b log base b of n time, right? I mean, you can build every level at least in linear time, right? Like one scan and you can bring every level. But you can actually do all of the B tree in linear time. Okay. So what you just saw so far was a static B tree, right? The data was sorted, you built a B tree on it, and then we were doing searches, right? But as I said, if we want to sort the data using a B tree, we will have to do insertions, or generally, we want to allow insertions and deletions. So now, whenever you Google for a B tree, right, or you look at the description of a B tree, it will not say that every node has B children. What it will say is every node has between, B over 2 and B children. So have people heard of an AB tree? Was this something that was taught in your data structures? No. Okay. Well, then we don't really need to go into it either. If you had, then I could have used it. But so basically, every actually for the root, I think. Right. So, I mean, why? So, okay, can someone tell me why do I need to change the degree of a vertex? Why is now the number of children something between B over 2 and B? I mean, once I keep inserting things, right? At some point I'll need to split things, right? Or if you keep deleting things, at some point you'll have to merge it, right? And when you do the splits and merge, your degree may change, the degree of an internal node. So for example, when you're inserting a key X, right? How do I insert an X? Well, I search for X as before, right? So I have a B tree already. I search for X. I find the block in the last layer where X is to be inserted, right? And then if that block has space in it, I insert X, right? But if the block becomes too large, meaning, if the size of this block exceeds B or 2B, then I split the block into two small blocks. Now, when I split the block into two small blocks, this may trigger a change to the parent of these blocks, right? Because now its degree may become B plus 1, right? If its degree before was like, I don't know, B minus 5, then that's fine. Even when the last layer block was split, now the parent has one extra child, but that's fine, right? Because its degree was B minus 5, now it's B minus 4. The invariant is still maintained that it's between B over 2 and B. But at some point, if I insert too many keys into these blocks, then this parent, right, its degree will exceed B plus 1, and then we will split the parent. And these can trigger changes all the way to the root. So that's how you insert. And when you delete, and if the block becomes too small, then you merge the two adjacent blocks. So it's basically insertion and deletions. They will all take log base B of n IOs. And I will leave it as homework for you to look at the pseudocode.
Professor,
Yeah.
when we're merging two incomplete blocks, like if both of them are less than n over, no, never mind, it wouldn't make sense. Because if we're merging them, right, both of them would need to be less than n, I mean, b over 2.
Right, yes.
Okay.
So them are less than B over 2 and they have the same parent, then you merge them, and now that parent just has one child instead of two children.
Yeah, so it won't exceed b.
No, it won't exceed B.
Okay.
Merging decreases the degree.
Okay.
If the parent's degree becomes less than B over 2, right? Once you have two parents whose degree is less than B over 2, then you merge those parents into one, right? Because then together they have at most B children. So these are implementation details, but they are important to know how to do insertion or deletions, how to do these splits and merge. So with that, you have seen your first data structure in the external memory model, the B tree, that does searching, insertions, and deletions, all in log base B of n IOs or block transfers. Questions about this? Okay.
Yeah, I have a question for the insertion there. So I'd like to clarify that. Okay, so if the size when you insert an element and if the size exceeds B, then you split the node. Then do they go into the like next level, or how they stay in the same level? I don't.
Those two stay in the same level.
Okay. Mm, mm, I see.
And the parent now gets two children.
Yeah.
At
Yeah,
some
but then wouldn't they like affect the next level though?
It can if the parent's degree becomes more than B. That's why we allowed degrees to be between B over 2 and B. So the parent's previous degree was B minus 5. This is what I was saying.
Mm-hmm.
Then even with one extra child, it's fine. It's B minus 4 now. The invariant is still maintained, right?
Uh-huh. I see. Okay.
But at some point, if the parent's degree is split, if the parent's degree becomes more than B, then the parent needs to be split.
Okay.
Right? So this can trigger a change all the way up to the root. And then you will have an extra level, right? The root will become now 2, you will put one more, and then you will connect it to the other.
Yeah, okay.
I think there are very simple pseudocodes. I can send you guys. Maybe the original paper should certainly have it, but people have been implementing this so many times that if you want to see code, you can also see that pseudocode for this. Okay. So next we move on to sorting. So the problem should hopefully be clear. I have an external memory. I've given you n keys that are not sorted. Your job is to sort them, and then obviously the sorted set also you cannot store in internal memory. Internal memory you only have m amount of space. So your job is to bring the unsorted data in, sort it somehow, write it out, so that at the end what I want is all of these n keys sorted in external memory. This makes sense? Does the problem make sense so far? Any questions about the problem statement? It is sorting. I'm just trying to say you have to write out all the unsorted data in a sorted fashion. You can't store all of the unsorted data in your main memory. You can't do that because your main memory is way smaller than 10. Okay, so step one. So we'll now look external merge sort. If people remember merge sort, this will be basically an M over B way merge sort. So remember, M is the size of the main memory and B is the size of a block. Right? So clearly M is more than B. We will actually assume M is more than 2B. But that's not a major assumption. M is typically an order of magnitude more than B. So in step one, what we will do is we will bring in runs of length M. So when I say a run of length N, I mean you have your data N, right? Bring in every chunk of size M into your main memory and you sort it. And that sorting cost in main memory we don't count, right? So how many IOs do I do to bring in a chunk of size M into main memory? M over B, right? Because how many, I mean, in one IO, you can bring in B things. You have m things, you need m over b ios, right? So every chunk of size m, I pay m over b ios, bring it into memory and sort it, right? And how many chunks are there of size m? Wait, this is all like simple division stuff. So yeah, so n over m, correct? So for each chunk of which there are n over m many, I will pay m over b ios. The cancels. So basically in n over b ios, which is the scan bound, what have I done? I have taken my unsorted data and I have made sure that every chunk of size m is sorted. Does this make sense to everyone so far or not? Right, Arvind, yes. N is the full size of the disk and m is the size of the chunk. But b is the size of a block. So you can only bring in b things at a time, but I keep bringing in b things until I have a full memory load of size m, and I sort that memory load and I write it back exactly where I bought it from. And then I take the next m things, I pay m over b ios, bring in them in sizes of b. Once my memory load is full, I sort it, I write it back where it came from. So every chunk of size m, I pay these many ios to sort it, and there are these many chunks. So in total, I pay n over b ios, and now I have every chunk of size m sorted. Is step 1 clear?
Professor, I had a question. So when you're taking in the chunk of size B, like and you're doing that m over b times for each size m chunk, when you write it back, how do you get it so that the entire size m is sorted? Because that size m is bigger than size B, right? So you have to like
No. So originally my main memory is free, right?
oh, I see.
Right. I mean, we can start with an empty main memory. You bring in the first B elements. That's one block. You don't do anything with it. You bring in the next B elements, one block. You don't do anything with it. After m over b many block transfers,
Oh, I get it. Okay.
your memory is full. Now you sort the memory and write it back.
Got it. Okay.
And you'll do the same procedure that many times, n over m many times. That's a total of n over b ios. So now we have made sure that every chunk of size m is sorted. So we move to this picture below. So the first chunk of size m is sorted, the second chunk of size m is sorted, third chunk of size, all these are sorted chunks of size m. Okay, I've just stacked them one on top of each other because what I'm about to describe will make sense more like this. So I have, so is it clear that this is the picture after step 1? Any questions about this?
So when you say like m sorted, right? M sorted represents like whatever's going into the main memory, it's getting sorted, and there's B chunks. There's size B chunks going into the main memory, right? So once
size B chunks will go into main memory, but I will stop once I have main memory is full.
right. So once we have main memory full, that means that we start sorting it, correct? Or do we sort after each block?
No. You sort once the main memory is full. Yes. You sort.
So once the main memory is full, okay.
Right. Once the main memory is full, you sort. You pay m log n in sorting, but no one is caring about the comparison time in this model, right? No one cares how long it takes for you to do stuff in main memory.
Yeah.
So that sorting gets for free, and now your memory load is sorted. And now again in m over b ios, you dump that memory load exactly where you brought it from.
Okay. Makes sense.
So every chunk of size. So at the end of step 1 now, every chunk of size m was sorted. Basically, I brought in the unsorted chunk of size m into main memory using m over b ios, sorted it, and then wrote it back again using m over b ios. So I guess technically I should put a 2 here. One for bringing it and one for writing it, right? Maybe this will be Maybe this is more accurate, which is a 2, but in big O notation, I don't care. 2n over b is big O of n over. Right, so 1 is for bringing it in, and 1 is for writing it. Good. So now we have these. So I'm going to call each of these chunk of size m that is sorted. I'm going to call them a run, right? So that's a sorted run. And now in merge sort, right? If you go back to 323, what did you do in merge sort? You took your data, you partitioned it into 2, right? Now assume that these 2 chunks are sorted, then you merge them, right? By using this 1 pointer at the beginning of each of those 2 runs and advancing the pointer. Does this make sense to everyone, what I just said about merge sort, or no? In normal merge sort, we divide the array into 2, sort each of the 2 subarrays, and then we merge them, right? Here we can do more. So here, instead of merging 2 arrays, right, you can merge more. How many can I merge, right? So what I'm going to do is I'm going to merge m over b many runs. So why m over b, you'll see in a moment. So if I take m over b runs, right, and I bring in the first block of each of these m over b runs, right, then everyone agrees that now my main memory is full, right? Because I have m over b runs, and from each run I've brought in a block. So the total elements I have now is b times m over b, which is m, and my main memory is full. Is this step clear? Instead of the 2 runs that merge sort merges, we'll take that many runs and bring in the first block of each of those. I know this picture might look bad because usually the smallest is here and the largest is here, but imagine that my array is sorted like that way. So these are the smallest elements of each of the runs. I bring in the first block of each of these runs, right? And now we basically do the merging, right? So now what we do is imagine having m over b fingers, right? One at each of these first elements of these b blocks, right? And now you start an empty block where you write down whichever is the smallest of these m over b fingers that you're pointing to, you'll write that element as the first element, and you will advance that pointer by 1. And every time you will write down the smallest element where these m over b fingers are pointing to as the next element in your block. And once the block is full, you write it out to disk. Right? Once one of these pointers reaches the end of that block, what do? You go and bring in the next block from that sorted chunk of size n. Did this make sense or no? Do you want me to explain this one?
So once the pointer reaches the end of one of the blocks, you write back what you merged so far and then bring in a new block. Is that it? Or
Right. So you keep writing blocks as you manufacture them, right? So blocks are size b, right?
okay.
You keep writing blocks out as you manufacture them. And so originally these m over b blocks in memory are 1 each from the m over b runs, right?
Yeah.
And now once because what can happen is one of these blocks could get used way faster than the other blocks, right? Because maybe all the elements here are smaller than all the elements here or something like that. So you will write down these elements in a block, and then what you will do is you will write it out, and once the block of a particular run becomes exhausted, then you go and bring in the next block of that run. And you should move your pointer to the first element of that block. And now you again have M over B pointers. Keep doing the same thing. Write down the smallest element. Keep writing down the smallest elements until either the block you are writing to becomes full, in which case you evict it and start a new empty block, or until one of these M over B blocks is exhausted, in which case you bring in the next block from that run. So at the end of this procedure, what you would have done is you would have written down, right? So, okay, so actually maybe let me ask this. So at the end of this step, the blocks that I've written out, what will they contain? What have I achieved at the end of this step?
They'll contain sorted M over B blocks.
M over B block. So
Like
now,
within each B block, there'll be like sorted M blocks in them.
I mean, I would have actually ended up sorting all of this green stuff, is what I'm trying to say.
Hmm.
At the beginning, I'll bring in the first block of each of these M over B many runs, right? And I'll keep doing this. And once I run out of a block, I'll bring in the next block from that chunk, right? And so
Right.
at the end of the day, I will exhaust all the blocks for every chunk, and I'm basically merging them. Right? And so what I would have written down all the green stuff in a sorted order. Does this make sense to people?
I'm still trying to understand that. So,
Mm-hmm. So tell me the first step of this merging procedure.
all right. So, you bring in the first blocks of M over B runs.
So a run here is a row, basically, right? One of the sorted chunks of size n. That's what I mean by a run.
Yeah.
So I take the M over B runs and I bring in the first blocks.
Okay, and you and then they are sorted, and then where do they go?
Write them out.
Write them out where? Do you need an extra disk or memory? I don't know. I don't think I'm following.
Okay. Maybe you have. Are you worried that you're running out of space? That's why.
Yeah, yeah.
Good. Okay, then fine. Don't do M over B runs. Don't do M over B minus one run, and keep one block free. Maybe.
All right.
Does that make your life easier?
Okay, and what do we write in that free space? Only the pointer to the block?
The element. So okay, you have M over B minus one previous blocks, right?
Yeah.
Put your finger to the first element of each block in the beginning, right?
Yeah, yeah.
You have these many fingers.
Uh-huh.
Get the smallest element that any of the finger is pointing to. The smallest element among these many fingers.
Uh-huh. Uh-huh.
Write down that element as the first element in this new free block.
Okay, 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 okay.
And
Okay.
advance whichever finger you just used, advance that finger to the right by one.
What was that again? So I understand that the smallest one goes to the free space that I understand, and then the next step is what?
The smallest one was from one of these fingers that you were pointing.
Right, right, right.
Advance that finger to the right by one.
Yeah, yeah,
Now do the same thing.
yeah.
Once you have written down B smallest elements, this free block is now full, right?
Mm-hmm.
You write it to external memory
Right.
in an empty block.
Right.
You keep doing this business.
Okay.
When will you get stuck? Now, when one of these fingers reaches the end of one of these original blocks, right?
Mm-hmm. Mm-hmm.
In that case, that block was from some run. You bring
Right.
in a block from that,
Mm-hmm.
and you continue doing the same procedure.
Mm-hmm.
And you
Mm-hmm.
keep doing it until you have brought in all the blocks of all of these many runs.
Mm-hmm. Mm-hmm. I see.
This makes sense?
Mm-hmm.
So at the end of this step, I would have sorted these many runs, each of length m.
Mm-hmm.
Here. So at the end of first step, I would have like m squared over b many sorted. Right? At every time, I am taking m over b runs, each of size m, and sorting. That's my first level, right? So at the end of first level, or actually, I mean, at time 0, remember, I had every chunk of size m sorted, right? Now, my situation in external memory looks like every chunk of size this is sorted, right? Because I merged m over b of the first chunks of size m. Then I merged m over b chunks of the next chunks of size m. So now my external memory looks, my runs get longer, right? My sorted runs become longer from m. They now become m squared over b. Does this make sense? Does it make sense that my sorted runs are becoming longer? Originally, I just had m, right? Now I merged m over b many of those runs. So now my sorted runs are of length m squared over b. And now what do I do next? Again, I take in m over b of these runs and I merge them exactly the same way as I said before. And so after this step, the size of my runs will become m cubed over b. And again, I take m over b runs, each of size m cubed over b, and I merge them. And I keep doing it until I have the final sorted run. How many phases will I have? Well, every time, so my size of the run after the first phase, for which I paid n over b IOs, my size of the chunk, my size of the run was m, right? That's what we did originally in the beginning. That was this thing, this part here, right? So after paying these n over b IOs, we had made sure that every chunk of size m is sorted. That's a run. At the end of the second level, the second phase. So remember, in all of this, right, whatever I described here, every block is brought in at most once, right? I never bring in a block again. Once I bring in a block from a run, it's exhausted and it's done, right? Then I move on to the next block. So how many IOs do I do in one merging step? Well, I bring in every block once and I write down every block. So it's n over b, n over b. So that's again an n over b IOs. And now my size of the run has become m squared over b. After phase 3, for which I also paid n over b IOs, right? This is phase 3. Right? I'll bring in m over b runs. I won't bring in the full run. I'll bring in the first block of m over b runs, and now each run is m squared over b, right? Because that I did in the previous run. So the size of the run becomes m cube over b. How many levels will I have? Well, every time My size of the run is basically increasing by a factor m over b. And I stop when my size of the run is L. So it's basically m times m over b to the L should equal n, right? My starting run size times the factor by which I'm growing it every time to the number of levels. Once this reaches n, I'm good to go, right? And so this will give you L to be log base m over b of n over m. Which is, big O notation is the same as log base b of n over b, right? Because you can take log base b of n over m, and you can just divide by b, divide by b. Oh, sorry, not log base b, this is log base n over b. And you get log base m over b of n over b minus 1. Right, by the, well, I don't know what you call it, like log of a divided by b is log a minus log b, right? So that's log of blah divided by blah. So it's log of blah minus log of blah, but that's 1, right? Log base m over b of m over b is 1. That's to say this is basically the same as that. So that's our number of levels. And on every level, I do n over b amount of work. So that's how much work I do on every level. That's the number of levels. And that's my sorting cost. Okay, so where did I lose you guys? This,
I got confused. Can you go back to the previous slide? Like someone else asked, where is the sorted getting stored at? Is it going back to secondary memory or is it going back to memory?
yeah, it's going back to secondary memory. Yep.
Okay.
Remember,
And then
in the first step, when we
Mhm.
got in a memory load, we sorted it and we wrote it back, right?
Mhm.
The purpose of the first step was to make sure that whatever this unsorted data is, now after the first step, every chunk of size m is sorted inside, right?
Mhm.
Now in the next step, I'll make sure that my full data is still unsorted, but I'll make sure now the length of my run, which was m, becomes m squared over b. How do I do that? I took in the first m over b runs, right? So that total green space
Mhm.
is m times m over b. So that's m squared over b. And I'll merge all of these runs in one shot, right? By this algorithm that I just mentioned. I bring in the first block of these m over b runs, have a free block. I keep writing out these blocks, right?
Mhm.
Blocks I keep writing out, and I'll stop it when I have exhausted all of those elements in the green space. So all of these blocks that I would have written out by that time would be one long sorted chunk of length
Mhm.
m squared over b. Because I've merged
Okay.
all of the, basically I've sorted all of the green stuff.
And we're not sorting in place. We're sort of creating a new array, right? Or no?
Yes, yes, yes. We're creating a new array. Yes.
Okay.
But
Professor.
it is infinite, so we don't care about space there.
Okay.
Professor, I had a question. So, basically, each step you're doing the same thing, but the length of the run is getting bigger.
Exactly. That's
Okay. But you're still doing m over b runs each time?
I'm still doing
That's
each time because I need to bring in a block from each of the runs, right?
yeah,
That's m elements, m over b times b. I can't merge
Yeah.
more because then
Yeah.
my method, right?
Also, so if you were actually implementing this, would this be like a recursive algorithm where the base case is when like at the first step where we only did size m runs?
Right? No, actually, this is the algorithm. You run it the way I told you, right? You pay that many IOs, you sort each chunk of size m, then you bring in the first m over b block. So this is actually, I mean, I guess I don't know how to go. It's not really recursive in that sense, right? It's going bottom up.
Okay. Got it.
So if you understand this algorithm, then this table should make sense to you. In the beginning, the size of the runs are n, right? Like this. At the end of the first phase, I would have sorted all the green stuff. I mean, there'll be many green stuff, right? So once I'm done with this m over b, then I bring in the next m over b runs, right? Then I'll sort this, then I'll sort finally this. So m squared, so then the length of my runs becomes m squared over b at the end of the first phase. And again, I never bring in a block more than once, and I never write out. The amount of stuff I write is exactly the amount of stuff that I bring in. And that's everything once. So that's n over b IOs. Now when my length of the runs are m squared over b, again, I do the same thing, right? I'll merge the first m over b runs. Maybe this picture looks weird because I'm only mentioning 2, but this could be more than 2. Right? And when these are sorted and written out, then I move on to the next m over b run. So every time I merge the runs, my length of the stuff that I wrote out is multiplied by a factor of m over b, right? I would have merged m over b runs, each of size m squared over b. So when I merged all of these, I created one long array of length m cube over b. And then when I merged the next m over b of them, I again created another m cube over b. So I'll have those runs sorted. And I keep doing it until I have everything. So until my run is of length n. So to calculate how many phases I will have is this formula. Basically, you'll have log base m over b of n over b phases. And in each phase, you do a scan. You just scan through the data in each phase. It's just, the whole game is how you scan through the data, right? I mean, your entire data is here. How am I scanning it? I'm taking the first m over b runs, scanning them like this. And then I move on to the next m over b. So in every phase, I'm just doing a scan.
How did you get the equation there? M times m over b raised to the power of L?
Right. So my starting run was m, right?
Yeah, yeah.
In every phase, I increase its length by m over b. Right?
Yeah,
Because that's how many runs I merge, right?
yeah.
Take runs of a certain size and I merge m over b of them, I will create a run whose length is m over b times one of the run's length, right? One of the original.
Hold on. So your the denominator is b or b to the some power in the table.
Oh yeah, you're right. So this is actually, yeah, so it won't be m cube over b, right? This is going to be m squared over b times, so it's going to be m cube over b squared, right?
Uh-huh. Okay.
Right, so that's a good, because how much stuff is in this green right now? It's m over b runs, and each was length m squared over b, right?
Right.
So that's m cube over b squared, right?
Mm-hmm.
But basically, every time you multiply by a factor m over b. So this formula is
Right.
my
I
starting.
see. Yeah, that makes sense.
Yeah, but this was right. Yeah, it should be a b squared here. Every time you multiply by m over b, and you calculate how many phases starting from n until you reach n, and you'll get this. Basically, the base of the log will be m over b, because that's how many runs you're merging at one time.
Also, I have a question for in the previous slide. So yeah, so so all the first blocks of all the first blocks are now brought to the main memory, and now you're finding the smallest block, right?
No, not the smallest block.
I mean, yeah, you're creating you're finding the smallest, how do I say that? Not the smallest block of them, but you're finding the smallest one, and right?
have one finger in each block.
Right, right.
Smallest finger, and in
Right.
the right by one, right?
Now, yeah, right. Now that will go to right, that will directly go to the external memory again. That part is a bit unclear to me.
What will go to external memory again?
So I understand that yeah, I understand that from each block you find the small, I mean you find the smallest one and create a block of size B, right?
I keep writing elements in that free block, right?
Right.
And
Now and that is that had size of B.
now you write it out in external memory. This will be the first block of
Mhm.
of this run.
Right. Now my question is, now my question is, so that part, so the new one replace which blocks in the first phase?
Nothing is being replaced. Your external memory is infinite. You
Okay.
what you want. You write it in the boondock. It doesn't matter, right?
Okay. Then yeah, that makes sense. Yeah,
Right.
right.
Where, and that first block that you wrote is the first block here.
Okay.
Does that make sense? That would be this block.
Yeah, that I understand, but I was trying to understand how that will go to that position.
No, it will not go to the position. No, it will be a new array of
Mhm.
runs of these lengths sorted.
Oh, okay, then yeah, then I'm good. Yeah, thank you.
I'm sure people have figured out some way to save space, but external memory is infinite. You can
Okay. Okay.
but again, you can do it, and then maybe you can delete the previous one, right? Once you
Yeah,
have
yeah.
this, then so I think you can do it all using at most 2n space.
Yeah, exactly. Yeah.
That's fine. Yeah, it's
Yeah, thank you.
okay. Other questions about this M over B multi-way merge sort? Okay, if not, then we will stop here, and we will meet next. So next week is spring break.